Welcome all of you to the second lecture of Professor Muthukumar. So today's topic, I think, is Landau-Ginzburg theory and structure-phase separation. Is that correct?
I don't believe so.
Okay.
We were so behind.
Yes. I see. Okay. We'll see.
We had to catch up with what we did.
Okay.
And then we'll try to get there.
Okay.
Maybe next lecture.
Okay.
Sorry.
Okay.
When I gave the syllabus, I was too ambitious.
I see.
Okay, so without too much of a repetition of the argument, what we did was this. For a mixture of one kind of polymer with another kind of polymer with a different degrees of polymerization, we derived this formula. Where phi 1 is equal to N1, capital N1, N1, capital N1 plus N2, capital N2. And phi 2 is equal to 1 minus phi 1 because of the incompressibility. N1 is the number of molecules. N1 is the number of monomers in one chain of type 1. N2 is number of molecules of type 2, and capital N2 is number of repeat units, number of monomers per chain of type 2, right? And then this one is the total number of sites in the lattice. There are no empty holes in the lattice. That's what we did. So this is for a two-component system, and we can generalize this for many components easily.
Is there any general result for an arbitrary number of components currently?
Oh yeah, sure.
For any kind of polymer size or something.
These three generalized.
But on the other hand, I wonder, like, so is this result, like, is it for a fully jointed chain or for any kind of polymer?
No. Once we have DNA, like stiff polymers, then we have orientational degrees of freedom, and the same person who did this also did for semi-flexible rod-like polymers, Flory, around the same time, within a few years of Onsager. Onsager was athermal limit, high temperature limit, and Flory did with all temperatures, chi parameters. And we can talk about it maybe when we talk about microphase separation later on. Okay, so that was a starting point. And already, we discussed about the physical interpretation of the contributions of the different terms, right? The first two terms coming from entropy of mixing and that favor mixing, and this one is coming from energy of three different kinds of energies: 1, 1, 2, 2, 1, 2. All of them conspire together to give me only one parameter, chi parameter, which is, I should really to remind you, chi goes like some non-universal coordination number of the lattice by temperature, kBT, and then this is epsilon 1, 2 minus half epsilon 1, 1 plus epsilon 2, 2. That's what we have. Okay, so that's the summary of what we did in the last lecture. Okay, so now why do we even talk about this when we talk about LLPS if it doesn't have enough insight to quantitative insight that it can offer to us, right? So what would be the natural question we can ask? And qualitatively we were discussing about, well, chi is small, then everything is only miscible. There was a comment there, and we were thinking always in terms of miscibility, how to make them miscible. But we know when the biomolecular condensates, they don't like to mix, they make droplets. Therefore, we need to know the other question, what's the criterion for chi so that it would not mix? And that's the critical question, right? That means what would be the value of chi? Chi, if it's large enough, then large enough and positive, then delta Fm will be positive, it will not be negative. Therefore, it is not going to be miscible. So the question is how to get the critical value of chi above which things will not mix. Okay, that should be our goal, to figure it out. Let's do that. And before that, this simple expression has a lot of information buried, otherwise we would not be wasting time here, right? So it has enormous information it has buried. Okay, so if I take a mixture and I put some amount of one component, say, suppose I have liquid and I put one component, one polymer, one protein, right? One protein, not one molecule. Take a pinch of that powder and put it into this liquid. What will happen? You would think it's going to disperse, right? Why would that happen? Because when you take this pinch of your protein powder, it has a chemical potential which is very high because it's a pure material. When you put it in a liquid, it will disperse so that the chemical potential of that component is uniformly the same. Everywhere it's the same. It will be different value, it will be the same. So the driving force for this dispersion is the gradient of a chemical potential. Therefore, that is the one that's driving mixing or non-mixing. So therefore, what we should do is we should try to calculate the chemical potential. All right. Let me choose one component. Shall we choose component 1 as my label? So what is the chemical potential of component 1? Let me write mu1, and let's say at some concentration phi, say phi 2, right, and divided by kT. This is d delta Fm by kBt, partial derivative with respect to number of molecules of type 1. Number of molecules of type 1, keeping number of molecules of type 2 fixed and temperature fixed.
Why should mu1 be a function of phi 2?
You could choose phi 1. You want to choose phi 1?
Oh, you were just okay.
Phi 1 is 1 minus phi 2.
Yeah, that way. Okay.
Right.
I mean, that was okay.
Okay. You'll see in a minute why I write it as phi 2, because I'm going to take to illustrate the argument. I'm going to take the first component to be the water or solvent, and the phi 2 to be my protein or my polymer. I'm going to do it. Solute is number 2, solvent is number 1. That's why I'm going to do it. But as you know, the chemical potential is not an absolute quantity. It's a relative quantity. So you define this with respect to a standard state. That is a mu1. Now for the pure component, in the pure component, second component is not there. So mu1 is 0 here. Okay, so that's my definition. Similarly, you can define mu2 to satisfy Sandeep. Let's write it down. Mu2. Let me write phi 2. Happy? Now, please tell me what is the reference state for that one? 1. Right? The pure component, number 2. Right? Phi 2 is 1. Now, divided by kT, and that's equal to d delta Fm by kBt d N2 at a fixed N1 and temperature. Okay, so that's what it is. Such a simple baby equation, we can easily calculate this. Let's do it very quickly. So let me write delta mu1. Okay, delta mu1 phi 2 by kBt. Instead of writing the whole expression, I'm writing like this. Let's take the derivative of this. Please help me out. So derivative with respect to n1. So I have log 1 minus phi 2. Phi 1 is equal to 1 minus phi 2. Right? And then I have to take the derivative, chain rule, right? That's, I take this one. Then what I do is I have to keep that constant, n1, and the log of phi 1 would be 1 over phi 1, right? And the derivative of, let me write it down here because we are going to use this again and again. Phi 1 is equal to n1, 2, okay. I keep the denominator the constant. I take the derivative of this. I give this. Then negative n1, n naught square, and then take the derivative of this. That will give me n1. So this is equal to n1 by n0, total number of sites, right? 1 minus phi 1, and that's equal to n1 by n0 phi 2. Okay. Please check on me. I make mistakes. Okay. Okay. So d phi 2 by dn1 because phi 2 is 1 minus phi 1, derivative of d phi 2. Okay, so we got that one. So I have this one. So I have n1, okay, and then keep the n1, 1 over phi 1, and derivative of phi 1 with respect to n1, that's equal to, we just wrote down n1 by, what did I write down? n1 by n naught phi 2. Okay, we are done with this term. Let's try to do this one. That will be plus n2 1 over phi 2, a logarithm of this, that could be minus n1 n0 phi 2, the negative sign. I get that one. I'm done with this one. Now here chi, let me multiply n0 with the phi 2, right? With the phi 2, that would be n2 divided by n naught, right? So, right, let me take this is plus chi, right? And n naught times phi 2 will give me simply n2, capital N2, and then take the derivative with phi 1, and that's equal to n1 by n naught phi 2. Am I right? You don't agree with me. I make mistakes. We don't want to rush, right? We want to understand it. It is right. Okay, so this is equal to a log 1 minus phi 2. Okay, little n1, capital N1 by n0. Little n1, capital N1 by n0. That's phi 1. And here is phi 1. Phi 1 by phi 1 is 1. So we have 1 phi 2 from that term. And let's do this one. Okay, here I have n1, n0. Here I have n2 divided by phi 2. So I suppose I multiply capital N2 and divide by n2. Capital N2, little n2 by n0 would give me phi 2. That will kill this one. So what I have is a negative n1 divided by n2 phi 2 plus chi n2 by n0, that's phi 2 chi n1 phi 2 square, period. Exact, yeah. Okay, very simple general result. For two different lengths of the proteins, if I am trying to mix them together like a co-acervation, right? Suppose I am trying to mix them together, that would be the chemical potential. People were interested in this kind of a problem a long time ago. The reason was that they were interested in figuring out quantitative measurement of Avogadro number, what exactly the value of Avogadro number is. Okay. And the way they were trying to do was to measure osmotic pressure. Right? That's the way they were the classical physicists, right? For measuring osmotic pressure, they got Nobel Prizes in those days. Right. So the osmotic pressure in units of kBt is equal to, in terms of volume of a solvent molecule. Suppose it's really a solvent, right?
You haven't introduced that yet, right, in your
Okay. Let's do that now. Let's do that now. I'm going to take solutions. This is the general result, right? for solutions, when I say for solutions, one component is solvent. That means N1 is equal to 1. Okay. N2 is a polymer. Let's say N2 is equal to, it has say 160 repeat units or 1000 repeat units, some number. Okay. Let me consider that case. Two component system. One is a solvent, and its molecular weight is only 1 unit of the site that we are talking about. For a polymer, N2 is equal to a certain number, 100, 200, whatever you want, whatever nature tells you. Under those circumstances, we can say the osmotic pressure of the solution in terms of the volume of the site. Remember, we had a lattice, the volume of that site where one solvent molecule is going to sit in here. That's the volume of that solvent. That's equal to a negative.
That each monomer of the polymer has the same size as.
Yeah, that's the mean field argument. That's the mean field argument. Right. The negative of mu 1 phi 2 minus a mu 1 phi 2, this is 0 divided by kBt. So that's going back to elementary SATMAC, physical chemistry, biochemistry, whatever you want. So the chemical potential of the solvent is with the osmotic pressure with a negative sign. Therefore, based upon this, I have minus a log 1 minus phi 2 plus 1 minus 1 over n phi 2 plus chi phi 2 square. Okay. Square. It looks very pretty, and I'll tell you why. Right. For dilute solutions, suppose I have very dilute solutions like your problem, right? Suppose you have dilute solutions of IDPs, the proteins, whatever you have. For phi much less than 1, the osmotic pressure phi V1 by kBt goes like negative. Let's expand. Oh, negative. All negative. Thank you. It was k. Right. It is negative. So this is a negative. Logarithm of 1 minus phi 2 is equal to what? Minus phi 2 minus phi 2 square by 2 plus etc. Let's not worry about it right now. And then minus 1 minus 1 over n phi 2 minus chi phi 2 square. Right? Okay, so it's pretty. The reason is.
So the chemical potential that you're thinking of, really kind of an exchange chemical potential.
Yes. That is how much work you have to do to put one molecule into the system. So its chemical potential is defined as a Gibbs potential per molecule. G is a Gibbs potential divided by total number of molecules would give me the chemical potential. Number of molecules, independent of which molecule it is, what kind of molecule it is. But please look at this one, right? Now, what it does is minus times minus phi 2 plus, here I had negative 1 phi 2. Okay, this and this goes away. All right. Then the leading term is negative 1 over n phi 2. So that's equal to phi 2 divided by n. Okay. Phi 2 divided by n, going back here, phi 2 is little n2 capital N2 divided by n0. N0 is volume. Little n2 capital N2 divided by n0. That's my right. Then I'm dividing by n2. That's n. Then I'm getting volume density, concentration of number of second component. This is Fantoff's law. This is ideal gas law. Right? Fantoff's theorem, right? Fantoff's law. Okay, that's good. So that means we are doing something right. Okay. So then we go to the next step. Next step is, so negative, negative, so I get a half. And then I have minus chi phi 2 square plus etc. That's what we get. Okay, so this is cool. This is a Fantov. And this one, right, this is a colligative property, pressure, osmotic pressure, right, this is virial series, the ideal term, and this is a non-ideal term, right, like as in van der Waals, for example, but this is a virial series, and this is called a second virial coefficient, because it's coefficient of quadratic term of phi. Second virial coefficient. And what is that? Okay, second virial coefficient, right? And we know already, I think all of you know, you must have known, under theta conditions, we had a conversation the other day, under theta, so-called theta conditions, second virial coefficient is 0. That means, you know, when you have a chain, it likes to have all the extra volume interactions. If they happen to cancel out the repulsion and attraction, they happen to, you know, it's an accident. If it happens to cancel out, then the second virial coefficient will be 0, and according to this theory in general, that will happen when chi is equal to half. So it's not like a chi is slightly positive or something like. In order to get to that, even that state, chi has to be half or more, right? If it's a 0.1 or 0.2, still the chain will be chain will be expanded. It's already it will be thoroughly mixed. But in reality, if you do more advanced calculations, this is not true. The second virial coefficient is not that. Second virial coefficient gives me the molecular weight power in a good, well, let me write down 3 nu minus 2. This nu is called a size exponent, which we are not yet ready to talk about. So if I have a coil like this, and the radius of gyration of this coil would go like mass of this object power nu. For good solvents in the self-voiding walk, nu is equal to something like 3/5, close to 3/5. So this will show to be second virial coefficient would be, right, assuming it's 3/5, it will be n per negative 0.2, right. But the point is, it depends on molecular weight. According to this mean field theory, it does not have any dependence on molecular weight. It's simply half minus chi. Of course, here the prefactor will have half minus chi power something here. Okay. Why is that? The reason is the way this theory is constructed is by mean field. So we do not worry about, we did not account for any correlation, topological correlation. Right. Therefore, I should not expect this theory to work well for dilute solutions, because in order for the polymer chains to be completely mixed, so that you can assume it's a random mixing, the concentration has to be sufficiently large, and what we call overlap concentration. The concentration of the polymers should be larger than the overlap concentration, so they are able to interpenetrate, so they are able to self-average, they are able to mix well. Mix means interpenetrated well, so you can assume a random mixing approximation, right? Therefore, this is actually a very good way to remind us that I should not use the theory, Flory-Huggins theory, to looking for a phase separation and very dilute conditions, which doesn't happen anyway. So it's a moot issue, but still we should know this. Okay, so yeah. Please.
So this chi parameter, I mean, so second virial coefficient has to be 0 for theta condition, as you mentioned. So intuitively, one would expect this chi should be 0 to have the ideal condition, right? I mean, so chi is kind of giving us the effective interaction between the particles, which seems to be 0. If we take chi to be 0, we'll expect this is the ideal condition.
Just please pay attention to where the two factors come from. half is one factor, chi is another factor, and together they are 0. Not chi is not 0, half minus chi is 0. Why is that? That half is, let's trace back. That half resides here, this came from here, and this came from there, that came from there. That factor of half is of entropic in origin. All right. The other term is from the enthalpy, so they conspire together. So second virial coefficient is not determined only by energy, but determined by free energy. Right? That's the way. That's the reason we do this. So we can trace back where that notion is coming from. So you are right. Chi should not be 0. Half minus chi should be 0 at the theta point. So chi is equal to half. Please remember this. Chi should be half. So until chi is equal to half within mean field argument, everything will be miscible. Right. Okay. Now I can also write the similar expression for mu2. Right. Similar to this, I can write, do the same calculation. You can do this, or you can, by symmetry, you can swap the sign. 1 minus phi 2, you put it as phi 2. When you have phi 2, put 1 minus, phi 2, that's phi 1. Right. Inside n1, you put n2, and things like that. Right. It's very simple. You can do that. So no need to derive this. This is good enough. Now what I'm going to show is, what do you want to know? Let me say before I show. Why did we do this labor? What do you want to know? I want to know the critical chi. When does the phase separation take place? Right. That's what I want to know. Okay. How do you do this?
You say that you want to understand when delta X becomes positive, right? The corresponding critical value of it.
Not necessarily. We'll work it out. It's not a delta being positive. That's a necessary condition, right? The chemical potentials have to be uniform. I should not violate the fact that the chemical potential is the same throughout the sample. Chemical potential of one particular component is the same throughout the sample. Similarly, when they have two components, chemical potential of the second component should be the same throughout the volume. We'll work it out. But that's an important question, because normally we like to rush to say, as long as delta Fm is positive, right, it will phase separate. That's a condition, but that's not the only condition that we need to satisfy. Okay, so how do you do this? So let me take this expression that I had for osmotic pressure here. Let me take as an example. For this one, let me plot it out. Right? In order to plot this, I'm going to plot osmotic pressure as a function of volume fraction of the second component, namely the amount of the polymer. This is osmotic pressure, chemical potential solvent, right? This is volume fraction of the polymer, second component. So I'm going to plot pi as a function of phi 2. Okay. So what I'm going to draw is extremely important for understanding liquid-liquid phase separation. So please ask me questions, right? You don't have to assume that you don't feel shy. So I'm going to plot pi as a function of phi 2. So what do I have to prescribe?
But so while drawing it, I can also draw the free energy.
Yes.
And then I can take the actual, like, as a function of phi, and then I can start seeing, because then I'll this equation that you have just written, right, for the expression for the osmotic pressure, I'll be able to see there, because that's the derivative of that, right? Because that's how it's defined. So in that way, also I can think of it.
We can think of that, right? Okay. So if you do that, okay.
I mean, I'm not stopped.
No. But we'll do both. We'll do both ways. But since I have this expression here, I want to plot this one. Why do I do this? Because this is the experimentally measurable quantity. Right? Right. Free energy, that's a theory thing.
But I would love to see this. I mean, I haven't thought about I generally count on the other, but I would love to see this.
Yeah. But this is very important, I think. So let's do that. So here is my pi, V1 by kBT. I'm plotting this as a function of, let's say, phi 2. Okay. Now I'm going to take chi is half, right? I already kind of said chi is equal to half. When chi is equal to half, how is this curve going to look like? It's going to look like this, 0.5. Okay, you can plot, if you have a pocket calculator, you can plot it. It's going to be looking like this. What does that mean? It means that when I increase the polymer concentration, pressure goes up monotonically, which is physically correct, physically and intuitively makes sense. Suppose the increase is chi to, okay, before that I should have told you, I have to choose chi and I have to choose n, because these are two things I need to know. All right, I need to put n and chi. I chose chi there, and n is 1000 in this plot. And you can choose any number, you can plot it around. Suppose chi is equal to 0.3, 0.54. All right, chi is equal to 0.54, slightly larger. Then what I see is I get a curve like this. Okay. You must have seen this before, going about high school. You went to high school, didn't you? Or you jumped high school?
I generally, again, I think of the, I'm saying this is something I don't plot, so I'm just trying to.
No, that's not an excuse.
Then okay, my conceptual.
Pressure versus volume of a real gas, van der Waals.
Oh, yes, of course. Oh, sorry. Of course. Yeah.
First Nobel Prize in physics.
I agree.
Okay, so
but again, the problem is, as you were saying, is that so I'd like to think from there, and then I come here, and then I start drawing these lines, and so.
Let's
build. Doing it like this.
Let's build from high school stuff. Let's build intuition from this. Yeah, we want to be, grounded, right? What is amazing here is this is a beautiful lesson here, right? Between this point and that point, this is crazy. You increase the concentration, what you see is pressure decreases. You add more material, pressure goes down. That's a no, not on this universe. It's not going to happen. So this is a no. It won't happen. If I prepare a solution under this condition, chi is 1 over temperature, I already told you. Under that temperature, corresponding to this value of chi for a given chemistry, if I prepare a solution here, it will be unstable. You cannot do it. It will very spontaneously will try to get out into something else. Okay, and this is the origin of our liquid-liquid phase separation already, for example. Okay, it can't happen. Okay, so this point is called a spinodal point. I'll write it down in a minute. Okay, I'll write it down. This is a spinodal points. This point and that point. Between them, it is unstable. Then, if I look here at this value of pressure for this condition, right? I have one phase here with some concentration here, phi 2, some value. Another concentration here with different value of phi 2. They all have the same osmotic pressure. This point will also have an same osmotic pressure, but at that point is unstable. That cannot happen. So there are two points that will have the same osmotic pressure for this value of temperature. Similarly here, if I take these 2 points, they will have the same osmotic pressure. So between this point and here, between this point and there, I have a family of possibilities, but not all of them are allowed. Only one of those pairs is allowed. And why is that? The reason is I'm plotting only for the first component, chemical potential, the first component. But then I have to at the same time make the equality of the chemical potential second component. So what I need to do is I need to write down coexistence. That is mu 1 at phi 2 prime is equal to mu 1 at phi 2 double prime. At the same time, mu 2 phi 2 prime is equal to mu 2 at phi 2 double prime. That means there is going to be one point in here and another point there. They are going to be coexisting. Out of all the pairs that I could choose, there is only one pair that would satisfy these two conditions. Okay? And who proved this? I mean, there is a very simple trick. This is a Maxwell. Yeah, you do Maxwell construction. So what you do is very simple, right? The Maxwell construction is the pressure here is same as the pressure there. For going from this point to that point, d pi, integral of d pi is 0. So that means if I follow, instead of doing that way, suppose I follow along this curve, this path, and coming down like this, that can happen only if this area here is same as this area here. That's the equal area. But when you plot it, immediately you will know. Okay? That's the Maxwell construction. Okay, based upon this, we are going to consider a phase diagram. How do you do this? So I have, say, chi, all right, chi, and then I have phi 2, and at this value of chi, 0.54, which is somewhere here, 0.54 is there, for example, right? This red point goes in here, and this red point goes in here. Between these 2 points, no phase separation, no stability. It will not be miscible. But the actual coexistence will happen corresponding to this point and corresponding to that point. Okay? So if I quench the system into a temperature where I have the concentration anywhere between this LO point and this LO point, right, the system will not be miscible. They will form daughter phase, two daughter phases. The mother phase will give birth to two coexisting phases. One phase will have the concentration of phi 2 prime. Another phase will have the concentration of phi 2 double prime. These are two phases. Okay, if I increase chi, then this will happen more and more. Then what will happen is it will have a coexistence curve coming like this. The other branch.
I didn't understand the temperature part.
Chi is 1 over temperature.
Okay, so you are, yes, of course, but I'm saying that I can think of the interaction energy in terms of interaction energy as well, right? So
You could, yeah.
Because you were plotting chi.
Only chi. That's a good point. I'm plotting chi.
You're not, okay. Because it will be inverted there. I mean, if it's like the temperature.
I was going to write it, yeah. Assuming that energy is temperature independent. Okay, so now the point is between chi is equal to 0.5 and 0.54, there will be a curve, a temperature value of chi, which will look like this. And this is chi critical, 0.532 for this particular example. So this is the point of inflection. That's chi critical. That means these two, the van der Waals loops, right? These 2 points will be going closer and closer. Eventually, they'll merge there. Similarly, this one would come down and merge here. That's my chi critical. This is my chi critical. And similarly, this spinodal curve will also come down and meet there and meet there. So this is a spinodal curve, and this is the coexistence curve. And inside here, it's completely unstable. And in this region, it's metastable. And this is the critical point.
Could
you repeat the physical significance of those yellow point in the osmotic pressure?
The yellow point is the concentration of one yellow point is concentrated in one daughter phase. The other yellow point is the concentration of the second daughter. These coexist. If when you mix it, if you mix it in a way, the concentration, there was a question the other day, concentrations between those two at that chi value or corresponding temperature value, if you make a solution, try to make a solution between these two yellow points, right, that would not be stable. You cannot mix it. They will make these droplets, right? They will make a droplet. The concentration inside one droplet would be one corresponding to one yellow point. The concentration in the other droplet, which is in the background, will have a different concentration, that will be 5 2 prime. Okay, now that's predicted by this simple expression. This is why it's a very important expression. Why we are laboring this point, right? And you can imagine when you decorate with more chemical details, biological details, everything, the robustness will be there. You will be decorating more and more on top of that, but you cannot get away from this picture.
How did you get the 0.53, like that exact number? Is it something
Calculated it. I
It's
calculate.
from this, okay, from this.
Yeah, from this you get this.
You get
Yeah.
Okay, you're not.
I put different values of chi and I plot the graph, and then I find this. Okay. Okay. So, what is the condition for spinodal? Condition for spinodal is this, right? That corresponds, one red point corresponds to the maximum here, another red point corresponds to minimum here. So that means at the extrema, the first derivative is 0, right? But this pressure is already a first derivative of free energy. Osmotic pressure is mu1, and mu1 I define to be the derivative of free energy. So it is a second derivative of free energy is 0 at the spinodal point. The spinodal curve, spinodal point, is given by second derivative d squared delta fm by kt, or kt by d phi 2 square equals 0. So that's the criterion for the definition for spinodal curve. Now you know why it's a stability criteria. Okay. Comments or questions before I move on to next one? Still I have not answered what the critical value of chi is. See, now you see why when you were asking me the other day about what concentration you need to phase separate, right? What do you need? you should avoid this big region. Everywhere else you can mix them.
This is the phase diagram, right?
Yeah.
This will tell us all the answer.
Yes. Exactly. And you can predict it. You can make it. Now let's calculate chi critical. Okay. Chi critical, let's do this. How do you do this? Chi critical, I told you, is this one. Okay, delta, let me make life easy by, let me take n0 kt. Okay, so let's take general result, right? Instead of looking only at solutions, because we are talking about different kinds of polymers. So this would be phi 1 by n1 log phi 1 plus phi 2 divided by n2 log phi 2 plus chi phi 1 times phi 2. Okay, that's equal to, let me tell you, I'm going to take the derivative with phi 1. Say phi 1 by n1 log phi 1 plus phi 1 minus phi 1 by n2 log 1 minus phi 1 plus chi phi 1 times 1 minus phi 1. I want to write it only in terms of phi 1, because I'm going to, oh, you want to do phi 2? Doesn't matter. You could do either way. Oh, in this particular case, phi 2, sorry. In general, you will see the symmetry. In general, you could do other way. Okay, so let me write this to be f. Okay, df by d phi 1. Please give me a hand. Okay, 1 over n1 log phi 1 plus 1 over n1, then a minus 1 over n2 log 1 minus phi 1, and then I have negative 1 over n2 plus chi minus 2 chi phi 1. That's the first derivative.
So, I have a question. So, we have two regions, unstable and metastable. So, wherever in the unstable, it will go to two phases, phi 2 prime, phi 2 double prime. So, in metastable state, will it go to these of the two, or?
Same two phases will be the eventual states, eventual phases. The kinetic, we will do the last lecture, the kinetic pathway of how the daughters are born, right, would depend upon whether I quench the system into this region or that region. The pathway will be different. This will be nucleation growth, as we will see. This will be spinodal decomposition, as we will see, right? And but the eventual state at a given value of chi, it will be these are the ultimate phases. This will, if you quench it here, it won't stop there. It will keep on going here. Similarly, when I quench the system will give birth to these two phases.
Unstable will always go to two phases, but metastable has some condition to follow before.
No, they will also go to the two phases. They need a barrier. They have a barrier, and then that's easy to break. Yeah.
So in a certain temperature, these two yellow points can coexist, but won't.
Say again?
So in a certain particular temperature, these two yellow points will coexist, but won't no transition will happen in between.
No.
They are separated by the.
They are right, because in the inside, why would they try to do it? Because the chemical potentials are the same. So there is no driving for them to do anything more, because they are in equilibrium. Because that's why you see phi 2 prime first component and phi 2 double prime first component. In both phases, the chemical potential is the same for the first component. Same thing is true for second component as well. So there is no driving force for them to swap or anything like that. There is no need. Right? And that's the reason why these droplets are always lingering around. Right? You'll see. We'll see some.
Just continue this question. So you will be needing the eigenvalues and all these things by kinetics to know where which direction will be.
Absolutely. Yeah. We heard a very nice talk a little earlier, Lipmanov exponent and everything. So all those things will come into play if you pay attention to how these things happen, right? Because in nonlinear problem, yeah, let's see. Okay, so all right, so let's do. But I'm trying to do this, right? So let's do second derivative. D square f d phi 1 square please 1 over n1 phi 1. This is, it will not contribute, minus another one that will be plus 1 over n2 phi 2. That will not contribute, minus 2 chi. Okay. So you can very quickly you can determine your spinodal curve, which is this guy. This is my spinodal curve. If this quantity is equal to 0, that's your spinodal curve. What is amazing is the spinodal curve is determined, right, by only the molecular weight differences, one protein of certain length, another protein of different length, composition, and the energetics. Very quickly you can tell. Right. So, but even we don't have to do too much work. You just to know the chemistry, you can see how they are going to mix. All right. So, but at the critical point, okay, that's the spinodal curve. In the inflection point, what happens? Right. The second derivative is 0. The first derivative is 0. The second derivative is 0. But with respect to free energy, then the second derivative free energy and third derivative free energy must be 0. Right. So let me continue here. So d cubed f by d phi 1 cube would be equal to, let me go in here, a negative n1 phi 1 square. Okay. This is 1 minus phi 1, So if you don't mind, I'll write it again in a simplifying way, 1 minus phi 1. Okay, so let's do that again. So that will be plus 1 over n2 1 over 1 minus phi 1 square, right? Correct. That's it. Okay. So what I have to do is I have to take this to be equal to 0, that to be equal to 0, and we solve this. Okay. And it's easy to do. I mean, even by looking at this one, you can tell phi 1 1 minus of phi 1 is equal to what? That's equal to phi n2 by n2 by n1 square root. Okay. Okay. So from this we can calculate, this is critical value, right? So phi 1 critical is equal to, bring it in here, that will be square root of n2 by square root of n1 divided by 1 plus, there must be an easier way to do it, n2 by n1 square root of that, right? Yeah. And that would simplify to so the critical value of chi determined only by molar masses. Energy doesn't appear. The disparity in molecular weights. That's all matters. We are building intuition, right? You know, when you do, particularly when you do simulations, right? You cannot violate these theorems, right? Because simulations cannot run forever, right? So you need to be very careful. So we know phi critical. So you take that one, this expression, put this back in here, and you can get chi critical. Okay. Instead of boring you by doing the arithmetics, I can show you chi critical is equal to square root of n1 plus square root of n2 squared divided by 2 times n1 n2. You can do that, right? We substitute phi 1 c, and then 1 minus phi 1 is the indices get swapped. Then from that you can get divided by 2, you get this one. Okay. Once again, the critical value of the temperature or its equivalent is dictated only by the disparities in molecular weights. Okay. Now suppose I take 1 IDP in water, salty water, let's say salty point charges, salty water of certain length, say 140 residues, and I take another IDP in a solution and it has only 60 residues. Immediately you can tell how the temperature is going to be shifted, and the location of the critical composition is going to be shifted. So going back here, where the whole thing will be, warped. This will be shifted here, and this value will go up and down when you change this, when you compare different systems. And it has been verified for synthetic materials, synthetic polymers. This works very well. Okay. Any questions on this one?
So for biopolymers, have people tried?
Yeah, Alan Minton has done crowding agents, for example. No, it's still in a very early stage. This is why we are doing this, right? And now, so far I have not talked about long-range interactions. I'm focusing only on short-range interactions here. The long-range interactions, it gets very rich, very exciting, which we'll talk next week, Monday.
Because people do these in vitro assays all the time with biomolecules, right? So if one actually, this is something, this is something I thought about, but if I take, if I actually look at the size of these proteins and put plug in those numbers, does it give me any insight.
We should try. Yeah, it will give you
I haven't-
insight.
yeah, but
It will definitely give an insight. Particularly when you put salt, the long range interactions screened, then these things will become valuable. Yeah. Okay, so now I want to go further. Is that okay? What do you fix? Okay? Okay. Oh, it's not even an hour. Not even an hour. So we can go further. Okay. So I'm going to erase this now. Before I erase this, I want to draw one more picture because of the comments that were made by Sandeep. Now, in the real world, I want to put this is phi 2. This is temperature. Okay, and he mentioned that it's going to be upside down because chi is here, 1 over temperature. If these things do not have temperature dependence, suppose they don't have temperature
That should be also positive. Right?
Sorry?
That cofactor should be also positive.
Exactly. Yeah. We talked about this. The combination of chemistry and physics together should be positive. Right.
In half an hour, I was just wondering about that. What will happen if that is negative?
That we discussed.
We discussed this. I'm sorry, you're too late. How much can I say? If it's negative, then everything is miscible.
Yeah.
Yeah. Yeah, and the reason why it was negative, if it is negative, the bracketed term, that means 1 and 2 like to mix more. That's why it will be negative, because the epsilon 1, 2, each one of them is a negative quantity, amount of attractive energy, right? If 1, 2 is more attractive than 1, 1 or 2, 2, right? This is more attractive, then it will be negative. Then everybody is a happy world.
So Muthu, I have a question. So let's say we have like something like non-reciprocal interactions. So one likes 2 but 2 doesn't like 1.
Yeah.
In that case, like, what would happen? Like,
Well, the matter is politics, right? Right? It depends on how much one likes the other, right? Yeah. Yeah. Enemy of my enemy is a friend. Yeah.
But can you use this?
even, I mean, that's,
Yes.
that's another thing, right?
Yes.
Because this is again a free energy that you are writing.
Yeah.
But that system will, well, I mean, I don't know if it's always out of equilibrium, but for a large number of cases, it might go out of equilibrium. Then you cannot write down a free energy.
We are always talking about equilibrium situations here.
Okay.
So far.
Okay. In that case, you can, of course, do this.
right.
In fact, that is exactly this is exactly what I was asking in the last class, that you had this half counting thing that you were doing, right? So I was thinking if epsilon 1, 2 is not equal epsilon 2, 1.
That's a different problem, right? That's a different problem. So I have encountered and worked with, particularly when there's a chirality involved, and that's a problem. It's a signal. But then, 1, 2 is different from 2, 1.
This is something we encounter with some actin binding proteins.
That's non-equilibrium. That's non-equilibrium. Yeah. Temporarily. Yeah. If you wait long enough, then that will wash out. Okay.
But
Anyway.
that object, epsilon 1, 2, I was just wondering, we can choose very small number, right? That positive number, but very small.
Yeah.
0 plus.
Sure.
So chi critical can go to the can hit to the x-axis or not?
It can.
So like the people talk quantum critical, it can be like that.
Well, there are analogs with the quantum, right? I mean, which that you will hear tomorrow in another place. Right. Okay. So, right. So, what I want to do is I want to say that I will have this curve. That's my coexistence curve, right? Temperature versus phi 2. Because experimentally, this is what we play with. We increase the temperature a little bit, 37 degrees Celsius or 35, 25, 40, 10. That's what we play around, and we change the composition. So what I want to do next is I want to share with you how we think about the onset of the birth of the daughter phases. Okay. So that means when I make the solution, I'm going to be somewhere here. Right, the temperature is here, right? I'm going to be I'm going to be here. That's where I make my solution. It's happy. Everything is homogeneous. Right? Now, what happens if I lower the temperature? Okay. Does the system already know that there is going to be a catastrophe when I lower the temperature? The answer is yes. It knows. And how do we monitor that? How do we measure that? Measure it, compute it, right? Things like that. So that's what we want to do. That's what I want to talk about now. It will take about 15, 20 minutes. Oh, eraser. Oh, here it is. See you next week. Safe travels. May I erase this? First, let's draw a cartoon, and then we'll quantify that. All right. So I'm here. Let me plot volume fraction of this component as a spatial location, as a function of spatial location. This is spatial location, right? This spatial location is very large. Okay, this is only a cartoon. When I'm there at that high temperature, that means chi is very low. It's homogeneous. Chi is below chi critical, right? How would this density profile, concentration profile look like? Right? That will look like somewhere here. That will look like that. Because it's a finite temperature, there will be some noise there. That's what it will look like. Right? Now, if I bring it down, we know that it's not going to look like this. Right? There are going to be two phases, right? And if I wait long enough, so one would have. Let me draw this one. One would have phi prime. Other this is phi double prime. Let me say. And the other one will be phase will be phi prime. So it will look like this. That's one phase here, right? And it's a large system, and then there's an interface, larger system, and it will look like that. So the one daughter phase, high concentration, another daughter phase, low concentration. They are coexisting, and there's a meniscus. There's an interface. Okay. But in the middle, temperature, say for example, somewhere here, right? It has to be somewhere between here and here. So what happens is it will be very large fluctuations like this. Obviously, right? Without those fluctuations, it's not going to eventually make the daughter phases. So even before you approach the critical point, there are going to be fluctuations. So let's write down a generalized Flory-Huggins theory. So let's write down free energy density that I wrote down before, right? That's equal to dr, three-dimensional quantity V. Let me write local free energy, right? Free energy, local R, free energy functional, local R. Let me write like this. And how would I do this, right? I would do this one to be written.
Just trying to understand. So FR is the free energy density.
Yeah.
And the nu is the molecular. Sorry, is it nu?
That is a volume.
That's V. Is it V?
That is a measure, volume.
Oh.
Volume of the system. So the local free energy, right? How do we do this? I want to write the local free energy very much like what we did before, right? And there are going to be fluctuations. So what I'm going to do is I'm going to define the amount of fluctuation like this. So volume fraction at some location R minus location R minus some average value. Let me take that to be phi critical, because I know what phi critical is. Let me write this to be equal to, let me write this to be psi. You guys know this. This is called the order parameter, right? The psi at that location R. Okay. Or it doesn't have to be phi critical. You could also be phi spinodal. Right? You could choose or phi average value. But that number is not going to be that important. Right? Okay. So how would I do this? I'm going to do a Taylor series expansion. I'm going to write this to be, since for weak fluctuations, I will write this to be some constant plus d delta f, this is that f that I wrote down, df by d phi d square d phi. First derivative is 0, right? When phi is equal to phi critical, 2 factorial, and then psi square. That's the leading term. Plus next term will be psi to the 4, psi cube, psi to the 4, everything that you want. But please notice, when you do this, what happens is this. Here is a high concentration, here is a low concentration. So there is a gradient in concentration here. So when I have a gradient in concentration, it's like creating an interface. So there's going to be a penalty to create a wall between poor and rich domains. There's going to be a penalty. And that is related to interfacial tension. So there's going to be plus.
How can you create a wall?
I beg your pardon?
Creating a wall is what?
1 second. Sorry.
Creating a wall
Great interface, right?
they are not trying to if it is going to be
No, they like to be uniform. But we say we create, the system creates fluctuations. That means in one place the concentration is high, another place concentration is low. Whenever you have concentration high and concentration low, there is an interface, right? You have a cup of water. Above the surface of water, there is air or water vapor, and you have liquid water, so you have an interface.
Yeah, but you are coming from the low high temperature to
No, these are one temperatures. I'm just looking at one temperature. If you have a density profile like this, you will have an interface. Yeah, you have to have.
So why that 1 factorial to down?
1 or 2 factorial.
Why is that?
Taylor series expansion.
Okay.
And second derivative. All right. Okay. Now, what is this?
But Muthu, I mean, in principle, one can ask the gradient term can be linear, it can be all sorts of terms I can consider. Right? I mean, you are taking square gradient for this.
Why? Because whether I go down from up to down, low value, or that way, the penalty is the same. So it is symmetric in terms of whether I go this way or that way. That's why I take this square. Okay. And for the kind of gossip, this is called Ginzburg term. In superconductivity. Okay. And this is the leading term of a series of expansions in psi, and these are called Landau terms. And this kind of theory is called a Landau-Ginzburg theory, as was introduced today. Okay. I had to do all these things to get here. Landau-Ginzburg theory. And you can have psi 4 term, psi cubed term. If you have time, you can talk more about this. That's what it is. Okay, so what I can do is I want to now, right? I want to know now measure how this fluctuation is occurring experimentally. How do we do this? Right? How can you make a suggestion? I know people don't like measurements here in this building, except a few people, except him maybe. How do you do it? How do you measure it? How could you measure it? You know, you could probably put some dye and watch how it dances around. Maybe, you know, you look for some reflections in a water pool or whatever, you know. How do you do it? We do by scattering, right? This is the famous experiment of determination of Avogadro number, right? Which was inspired by Einstein's theory for Avogadro number, colloidal particles, Brownian motion. The way people did this was by light scattering. Okay, and how do you do this? The principle is the following. I have my sample here, and I send in a beam with the incident wavelength lambda, and you measure the intensity not in that direction, because the intensity is so large you will kill your apparatus. You measure it at an angle, theta. Here is your detector. You measure the scattering intensity, I, as a function of what is called a scattering wave vector, where k is equal to 4 pi over lambda sine theta by 2. Sine theta by 2. So people change theta, move the detector around for different angles. You know lambda, that goes in here, theta there. You can change your scattering wave vector k. That's how you measure this. What does it measure? This measures structure factor. S of k is called a structure factor. I'm sure you know this, right? Structure factor. What is structure factor? This is correlation function of, this is psi, this guy psi in Fourier space. That's what it measures. So this is the experiment. Experiment tells me this one. What we need to do is we need to provide this one. We need to provide that one from lambda Ginzburg theory. So what you do is you take this, we rewrite this f to be equal to half summation over k a. This is a. Let me call it a, which is this guy. Second derivative of free energy density with respect to phi 1 square. Phi 1 is order parameter that we have already derived this. Right? You should be really excited about looking at this because A contains this information. That's A plus Fourier transform that kappa k square psi k square. Pretty. Becomes very pretty, very simple. Very simple. So this is the lambda Ginzburg theory in the simplest way, and if you talk to some of our friends, it's a free field theory, right? Okay, so everything that we need to know is contained in here, because A depends on N1, N2 composition. We know that. Chi we do not know, but the bulb should light up right now. Maybe from the scattering measurements we can measure chi. Experimentally we can measure chi. Once we measure chi, then we can go through all these procedures and make beautiful predictions. Okay, so that's why we have to Dow child. Okay, so given this, what is the probability that I'm going to have some excitation psi k? That's Gibbs weight, right? E to the minus half A plus kappa k square times psi k square. Okay, it's Gaussian. This means psi k square is equal to 1 over a plus kappa k square. You can do the Gaussian integrals, right? Second moment of a Gaussian integral, you know how to do that, right? Yes? You want me to do it? You can do that. Good. Okay. All right. So this theory tells me, right? This experiment tells me I need to plot if I plot a reciprocal of I of k, taking this psi k square goes like 1 over this. So if I plot the reciprocal of I need more space. Reciprocal of I of k versus k square, right? Reciprocal of this is the reciprocal of this. Reciprocal of this is the denominator here. Okay, I will get a straight line, right? If I do my measurements, I'll get something like this. I cannot make a measurement at k is equal to 0. I already warned you, please don't make a measurement at theta is equal to 0. You can't do it. You make measurements at different angles, then if you extrapolate those measured data to 0 k, that intercept is a. That is equal to 1 over n1 phi 1 plus 1 over n2 phi 2 minus 2 pi. I know n1, I know phi 1, I know n2, phi 2, then I get 2 chi experimentally. This is the way we do. This is the way we do our business. Okay. In addition, the slope here will give me a kappa, interfacial tension. What does that mean? Going back to this expression, I could write this to be 1 over a 1 plus kappa by a k square. Can't I? I can, right? Sure. Okay. I could rewrite this to be 1 over a 1 plus. What's the dimension of 1? There's no dimension, right? It's a number. What's the dimension of k? Dimension of k, right, is 1 over length. Lambda is wavelength. So k square is 1 over length to square. That means kappa by a must be length to square. We write that length to square to be c square. And the c is the correlation length of the fluctuation. C is the correlation length of the fluctuation. Okay. And that c, I'll write it here, that c is equal to kappa by a square root. Okay. This is not new. This is more than 100 years old, right? And this is called Ornstein-Zenica, after the experimentalists who did this for the first time to find the understanding opalescence, critical opalescence. How we'll talk about it in a minute. How correlation length diverges with temperature, lowering the temperature. Okay, so this is called Ornstein-Zenica plot. Or Ornstein-Zenica expression. Okay, so what this means is the following. The intensity would diverge. Intensity would diverge when? Intensity is proportional to psi k square, and that's 1 over a, right? What will happen for this value here? This is 1 over a. That's what I'm looking for. K is equal to 0. K is equal to 0 here. right? A is this. When would intensity goes to infinity? Right. Suppose A goes to 0. A goes to 0, 1 over A, that goes to infinity. So what I would expect is when the chi value comes closer and closer to this number that I chose. I made my sample. When chi becomes equal to 2 chi becomes equal to this number, then A will be 0. That would mean, right, A is 0. That would mean second derivative is 0. Second derivative 0 means that's a spinodal point. So I make a measurement, right? I make a measurement of this, and then I change the temperature a little bit. I make a measurement again, like this, again, like this. And then there will be one temperature at which the extrapolated value hit this value, 0, because that is A is equal to 0. Extrapolated value. When that hits 0, that's your spinodal point. So you determine experimentally, you determine the spinodal point this way. Not only determine chi experimentally, you also get the spinodal temperature, experimental temperature, by making this measurement. In an analogous way, you make predictions, theoretical predictions, by making A is equal to 0, finding when A is equal to 0. That's the definition of spinodal curve.
Did they actually reduce the temperature and found the Xi to kind of slowly diverge or something?
Absolutely, we did.
Oh, you also?
Multiple times. We polyelectrolytes, charge molecules. Yeah, we do routinely. Okay, so, but now the question is quantitative. I'm going to stop in another 5 minutes. Quantitative description of how the divergence comes about. Okay, let's look at this one. I have now I can erase some of these equations, right? Because we have. Okay, if this is 0, I'm going to rewrite this to be 2 chi s minus chi. Second derivative is equal to, I combine all these things to be 2 chi s, because I told you chi s is the value of chi at which I get the spinodal point. Okay, when this is equal to 2 chi s, then I have spinodal conditions, right? Therefore, chi is equal to this number, chi s is equal to that one. Now, I already told you that chi within this theory is 1 over temperature. So this goes like 1 over Ts minus 1 over T. T is spinodal temperature. So this goes like T minus Ts divided by Ts. Don't worry. It's the depth, the distance of temperature from the spinodal temperature, which is in this notation, which is this one. This is T minus Ts. Okay. So I make these measurements at different temperatures, and then if it hits there, what will happen? If that hits there, A is 0. If A is 0, scattering intensity is going to go to infinity. So therefore, the scattering intensity will go like 1 over T minus Ts. That's the way it diverges. Okay, we write this in condensed matter physics. We write this with an exponent gamma, right? And a gamma is called a critical exponent. That's 1 according to mean field theory. But if you do renormalization group theory and more Ising model, exactly solve Ising model, make measurements, etc., the actual value is 1.26. Okay, the mean field theory gives you 1. When you put all the fluctuations that we know how to do it, make proper measurements, then that's what happens. Now let's look at the correlation length C. Correlation length C, I define in here. That goes like 1 over square root of A. That goes like A, I already told you, T minus Ts. That goes like 1 over T minus the Ts power half, right? Square root or half. let me write as a nu. This is nu. Okay, where nu is equal to half, according to the theory that we have done, Wundt and Zerniger theory, mean field theory. In real world, for real phase separations in IDPs and polymers, nu is equal to 0.63. But the point is, the fluctuation correlation length is diverging when you approach a spinodal point. Scattering intensity is diverging. Right? By monitoring how they diverge, we can tell how far away you are from the criticality, how far away before the birth of the daughter phases. You can gain. But you don't go into the daughter phases because you cannot measure chi when you go there. You can measure chi only when the system is homogeneous. So you make all the measurements there, and then you go and make predictions. Because in order to make the predictions, you need to know chi. I erased the Fourier expression there. It is somewhere there, right? So you need to know chi here. You know the composition, you know the molecular weights. You need to know chi. You make the measurements of chi. Once you have that, you can make measurement of your phase diagram. You can predict phase diagram. And of course, you can also make additional measurements to make sure your phase diagram is right. Okay, I think it's a good place to stop, and then you please feel free to ask me questions. So yes, we did cover.
So experimentally, like one of the way you told by this fluctuation of the density, free energy densities, basically. So can osmotic
the experimentally we measure only the fluctuations of the composite concentration. You cannot measure free energy. Free energy you cannot measure.
Concentration.
Local concentration fluctuations.
From like, can we also get this chi from the osmotic pressure? Osmotic pressure is also measurable in the solution.
Osmotic pressure in good old days. Yeah, osmotic pressure was the one people measured as long as the solutions would dilute. Right? It is very difficult to make measurements of osmotic pressure if it's a semi-dilute or concentrated. For protein solutions, in those days, that's what they did. You know, yeah.
I don't know experimental setup, so I think osmotic pressure will be easier. I mean, in the sense like there is a solution, we have two pedals that can go up and down.
No, it's very extremely hard, excruciatingly hard. Osmotic pressure, because the colligative property, any small particles number concentration is important. So anything that you have is going to contribute to the osmotic pressure, right? And so it's extremely difficult to make measurements. But people were heroic. People made, people got Nobel Prize for that, right? Osmotic pressure measurements. Yeah. But today, scattering, right? But there is a key question: how do does the light scattering work all the time? You should ask. Okay, light scattering will work only if the refractive index of the material that you are trying to probe is different from the background. Otherwise, the light scattering is not useful. So you need to have a contrast, right? If the contrast is not there for light, we do X-rays because the electron density would be different. If that's not going to work, we do neutrons because we can always deuterate. Technology has ability to deuterate set of them, and the difference between protons and neutrons is so big for neutron scattering cross section, and that will work. So the combination of light, X-rays, and neutrons, we can figure out all these things. Particularly for biological systems, light scattering and neutron scattering is fantastic. Light scattering is fantastic. Yeah. Why do you see a fish in a pond in water? Why is that? When you look at a fish, you see, oh, there's a fish. Why is that?
Scatter light and we can see.
No, the refractive index of fish is different from the water. That's the reason you see, because protein has a refractive index higher than water. So therefore, IDPs, yes, we can make measurements. We do in my lab. We make measurements using light scattering. Yeah, please.
The fluctuation of phi with respect to diffraction distance, does it also happen when creating constant phi? So is that
The fluctuations, you mean you are here? Yeah, everywhere. Here, if I start from here, I'll have those fluctuations growing here, boom, infinity.
And the fluctuations are highest at what point? Is it the closest to the
No, the fluctuation, that's not a well posed question, right? There is no, in every quench, fluctuation will be large. Yeah, everything is a candidate to have very high fluctuations because of the cartoon that I drew. Because this has to happen, right? Right. And this one, when I wrote down this one, that is for approaching those points. Okay. Until you get there, the fluctuation will be there. So, in order to address this properly, we'll talk about it in the next week. We will look at the contribution of fluctuations on top of the mean field theory. This is something that some of us are interested in. Okay, we did the mean field theory. This is very powerful to get insight and intuition and designing experiments, designing theory, designing simulations, and then checking whether our logic is our programs that we have written are okay, checking those intuitive results, validating on your simulations in terms of intuition. But for fine quantitative comparisons, you have to put in fluctuations in, because the intrinsic IDPs, unlike the folded proteins, they are highly dancing around, and that means the conformational fluctuations are there, and therefore the compositional fluctuation will also emerge from that. So fluctuations are important, right? Always at finite temperature. Only time that you don't have fluctuations is at zero temperature.
I was just trying to give the solution of all the fluctuations, how much
No, that's what we did. See here, the fluctuations are everywhere. You sum up all locations, then you resolve all those fluctuations into Fourier modes. That's your summation of k. We resolve them to Fourier modes. So you have a beautiful energy cascade here, energy spectrum here. All wavelength k is a reciprocal of wavelength, as we talked about, right? So you have energies with the different wave packets, and you sum them all up. That gives you free energy. Okay? But then, you don't measure free energy because you cannot do that. Then you get blank, right? So what you do is you measure for each value of k, right? And that way, that gives you information about how the fluctuation is taking place. And then overall, the free energy will be there. That gives you a phase diagram. By just measuring this alone will not give you a phase diagram. It will give you chi. I'm giving a strategy to get chi by making measurement of one wave vector k. Not one vector k, but change the angle, right? We plotted here. This is k squared. This is the brilliance of Wundt and Zernicke. Critical opalescence, 1906, I think, 1906, something like that. Crazy. Any more comments?
Next lecture will be beyond the Gaussian fluctuations.
The reason I'm hesitating is I'm not sure for LLPS, that is, the fourth lecture will have beyond Gaussian fluctuations.